Hi friends, welcome to follow up, and in this video we are going to look at problem 208, implement trie or prefix tree. This video can be regarded as follow up for problem 543 and especially problem 1522, N-nary tree, because a prefix tree or a trie can be regarded as a N-nary tree, right? So this problem, the current problem, that is problem 208, can also be regarded as a preparation or prerequisite for doing problem 3045, count prefix and suffix pairs 2. So this is a very interesting question. So we are going to implement trie data structure in this video, and in the follow-up we are going to analyze problem 3045, right? So with that said, let's look at the problem here. So we want to implement a trie. So this is also object-oriented programming, right? You write some class and then you encapsulate all the method or include all the method within this class. So here is an initializer. So this is down the method. So here we have insert. So we have insert our corpus in order to get a status of the trie. And also we need to be able to search for a word, whether given a string, to see if this string is a word in the trie. And also we can check, given a string, if it's a prefix, right? So with that said, let's roughly look at the problem statement. So here a trie or prefix tree is a tree, right? So first is a tree. It's a tree data structure used to efficiently store and retrieve keys in a dataset of strings. So yeah, it basically treats strings, but in some cases you can generalize it to make it retrieve say iterables. But we need the corresponding element in the iterable to be hashable, right? So there are various applications of this data structure, such as autocomplete and spell checker. So these are the two actually very known use cases. So we want to implement the trie class. So we have an insert method which inserts string into the trie, and we have a search, returns true if the string word is in the trie, otherwise false. And also we hope we can check the prefix. So with that said, let's also look at the constraint. So here the word length and the prefix length is bounded above by 2000. So this is basically related to the problem size, right? And the word and the prefix consist only of lowercase English letters. So we know that we have 26 lowercase English letters. This is also related to the problem size, right? Another one is that at most 3 times 10 to the power 4 calls in total will be made to insert, search, and start with. So with that said, I think we are ready to move forward to implement this trie data structure. So first, I think before you implement anything, you should have a clear picture about what you want to implement and some of the caveat points. So here I want to mention that first here trie. So it's known as prefix tree, right? Prefix tree, and especially it's an N-nary tree, right? Here. So for general tree, we can recursively define that, or in this regard we can see trie is also a recursive data structure. So with that said, you have two choices. So you can just use a dictionary to represent a trie node, or you can just write in another class so to get a trie node object. So we are going to do both in this video. The main consideration is that we want to understand the implementation and their slight variations so that you can get full digest. So with that said, first let's give an implementation that we do not use explicitly a tree node. So here I'm going to write one implement one that does not explicitly use try node, right? So in other words, I just want to use a dictionary to mimic a try node, right? So this is our plan for this one. And then we are going to make some slight variants. So for this, you can think, for example, you have AB and you have AC and you have ABC. It's something like this, right? So you have A, right? So you have a left child. So you insert this AB first. So you have A and B. So B is within dictionary A, right? Then you insert AC, but then you start from here, A, and then C is also a child of A, right? And then you insert ABC, but in this it will follow this path, right? Because C here is like this. So in this regard, so AB is it's both a word and also a prefix, right? So I hope that this very simple picture can help you build some some scenario. So basically you should make some drawings for yourself to digest that. That would be better. So here I'm going to do something like this. Root is a dictionary, right? So this is like I initialize here, right? Then we can look at this insert method. So the insert is used to build the try state. So basically what we want to do, so we start from the root and then we do the things. Let's see, in the recursive, in the for loop or linear scan of the word. So here, let's see the root. I'm going to set it to be the current root, right? So I'm going to start from here, right? So for character in word, so then there's two possibilities. If the character is already in word, right? So if character in word, right? So then we go next layer. So we are going to see root equals see root character. And otherwise, so we are going to do this. The original root and then character, we can make it another dict because it's because it's nested, right? And then again we are going to do this. Root equals root character. Then we go downwards like here, right? So once you've done this, so we want to mark this because we are inserting a word. So this current state of the root will also have a mark. Let's see. We can use something like this. End of word. So let's use it as true, right? So this finishes the insert method for this trail. And then we can look at the search and start with. So these two actually almost identical, but a little bit different. So we can write first the search according to the way we do the insert, right? So here, let's first set our root to be self root, right? Then we are going to scan the word. So for word, not for word, for character in word. And then we want to check if the character is in root, right? Or if it's a node, corresponding node. So basically, if character not in root, it means that this word is not in the try, right? So we're going to return false. So otherwise, the character is already in the current level. Then we're going to go next. So root to be root character. So if after this for loop nothing has returned, so it still does not mean this is a word, because we want to make sure it's a word. It can be a prefix, right? So then the point is that here, right, we have an end of word key, right? So we want to check if this key is in here and it's corresponding to true, right? So actually we just need to check in that, right? So I would just need to return if this key in root, in the current state of root. So this is the search. So now let's look at the start with. So this is for prefix. So first we get the root, the self root. And then what we are going to do is again follow this above. So for character in prefix. And then we want to check if character not in the current level, then we just need to return false, because it cannot be a prefix. Otherwise, so we are going to retrieve to next level, so root character, right? So, but afterwards, if nothing has returned, we can make sure this is the prefix, because in particular, a word is a prefix, right? So in this case, we just need to return true. So that's the difference of these two. One is, we check this, right? It's the more stronger condition. But here, once we we exit the for loop, we just directly return true. So I would say this is one way of doing the implementation. So here you can think of this dict. So you can establish a correspondence between a try node. You can imagine this is just a try node object. So this is basically how you think of the problem. So before we do some variants of the current problem, we can first do a test. So here, so keyword A, let's say root character, if character in word, not in word. So here is character in root, right? So we do this. Let's check. Yep, it passes one example. So now let's look at the generic case. Yeah, it passes all the cases. So I would say this is the one version. So I want to make some variants, because making some slight variants, it can be very important, because this will help you digest the code. So here I'm going to copy this one, and then I'll change this one to be the version we want, and then we are going to test this one. So here, we check this like this. So this is not very good, because the number of lines of code. So we can use some dictionary method. So I'm going to going to delete that one. So what I want to do is that, so I want to set the root, or I can directly do this. Even you can change this to be one. So we are going to set root equals root set default. So we want to check retrieve the corresponding dictionary for this character. If the character is not in the dictionary, so we're going to assign it a default value and return. So the default value is another dictionary object, right? You can do this, right? So this also resets the status of the root. So this actually saves a lot of several lines of code. So similarly here, but we don't need, because we need to return true or false. But this looks this is one variant, right? We can test that. And it passes all the cases. So I'm going to copy this again. I'll call this one version v1. So it's a slight change based on version v1. So next, what I want to do is I want to implement one that explicitly use try node object. So we don't use dictionary to mimic that. But I feel that this way is like add a wrapper above dictionary. So how can we do this? So you can, what you can do is that you can write a class, right? Write a try node. So I'm going to do this. So node. So I'm going to add an initializer, say self. So we want to add two attributes, say self offspring. So it's children. So we can use a dictionary, right? And then also we get a attribute for this node itself. That is, if it's end of word. If it is, so we're going to set it to be true, and then not, we're going to set it to be false. So for default, at the very beginning, I'm going to set it to be false. So this way we have a node, right? So next we are going to implement that. So here I'm going to make some changes. So first, I'll still get self root equals, I'm going to define it as a node, right? So notice that this root or this node object have two attributes or fields. One is offspring and one is end of words. So then we are going to do the insert. Let me comment this out. Then we write this so that you can make comparisons, right? So first we get the root is self root, right? And then what we are going to do, let's see, check the character for character in word. Again, we do the same thing, right? So we are going to use root, so offspring, right? So I want to do retrieve the corresponding key, that is character, to get the corresponding node. If this character not inside the offspring, so I'm going to assign it to a node value and then update the current root status. So this actually do a number of things together. And then after this for loop, we are going to set the end of word attribute to be true, right? So this is the insert, you can see, do comparison with this one. So now let's look at the search. So I'm also going to comment this out, and then we write the code here. So root will be self root. This is the same, right? But here's root is this root is a node object, and then we are going to check for character in word. So what we want to check is if character not in so root, we want to see offspring, right? So in this case, we are going to return false, corresponding to the line here. And otherwise, so we are going to set the root to be root offspring retrieves the current character. Then after this for loop, if nothing has returned, so we're going to check if the root, the end of word. So let's see, end of word is true, right? So let's see, maybe write like this. This may be better. So this is the search. So for the start with, I'm also going to comment this out and then make some parallel writing. So self root, and then for character in word. So if character, so actually we can copy, but let me tap that. For character not in root offspring, so in this case we for sure return false, and then we do root equals root offspring and the character. Again, after the for loop, what we are going to return is nothing but true. So we don't need to check this attribute. So if you compare the code that are commented and also the code here, so you will see the slightly variance, right? So this is another way of doing the implementation, right? So now let's look at the running. Word is not defined. Do you mean so for character? So here I see. So when we do start with, so I'm going to write prefix. Yeah, it passes one case. Now let's look at the generic case. Yeah, it passes all the cases. So here, yeah, we basically write some very direct implementations for the trie data structure. So overall, it might be helpful if you think of this trie as a prefix tree or tree data structure, especially I would say an N-nary tree. So that's also the connection of this problem with problem 1522, N-nary tree, right? And then after you can implement this trie data structure without referring to some references, then you can try to address problem 3045, count prefix and suffix pairs too. So that's this problem is a good use case for the trie data structure, right? So with that said, I would say that's about it for the current video. Thank you for watching.